Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So in today's lecture we shall study about the reason of difference in reactivity of alkanes and lower cycloalkanes. So the key concepts which we shall discuss in this lecture are ring strain, angle strain, steric strain and the torsion strain. So in the previous lecture you saw about what are cycloalkanes. So cycloalkanes are the saturated hydrocarbons having one or more rings of carbon as a part of their structure. So you saw about different cycloalkanes. So you also studied about cyclopropane, cyclobutane, cyclopentane, hexane, cycloheptane, etc. onwards. So just like alkanes form homologous series, cycloalkanes also form homologous series. So each member of the homologue differ from each other by a CH2 unit, right? Also you studied about the alkanes have a general formula of CnH2n plus 2, but if you convert a unbranched alkane into a cycloalkane, then you must remove two hydrogens, one from each part of the chain, right? So for example, if we have a cyclopentane, if we have a pentane here, you can see it's a straight chain, and you are to convert this pentane into a cyclopentane, then what happens, you have to remove a hydrogen from here and a hydrogen from this end. So by loss of two hydrogens you can convert an alkane into cycloalkane. So since cycloalkanes are formed from alkane by loss of two hydrogens, therefore the general formula for cycloalkanes is CnH2n, right? We don't add 2 because these two hydrogens have been eliminated when an alkane is converted into a cycloalkane. So cycloalkanes have two hydrogens less than its equivalent alkane. Just like if we have a pentane here, so if we count number of hydrogens, so 3 here, 2, 2, 2, and again 3 here, so we get 12 hydrogens here. But in case of the cyclopentane, we have 10 hydrogens here, right? So we have lost 2 hydrogens. So all the cycloalkanes have 2 hydrogens less than the alkanes, but still they are considered saturated. So why the cycloalkanes are considered saturated although they have 2 hydrogens less? The reason being that in cycloalkanes each carbon is bonded to 4 other atoms, right? So since each carbon is bonded to 4 other atoms, it means each carbon is singly bonded. Therefore we say that each carbon of this cycloalkane is saturated, right? So although there are 2 hydrogens less in the cycloalkanes, but still they are considered saturated. The reason being that in cycloalkanes, it's all carbons are forming 4 bonds to other atoms, so therefore the cycloalkanes are considered saturated hydrocarbons. So we have examples of cycloalkanes. So we have cyclopropane, it's a molecular formula, and you can see about the structure formula here, and this is line formula. Similarly, we have cyclobutane, cyclopentane, hexane, heptane, and this is general presentation of cycloalkanes. So you can see here from the molecular formula we cannot say anything about the structure of this molecule, but the structure formula, you can see this is giving clear indication that all carbons are having single bonds, and we have 2 hydrogens here, 2 hydrogens here, and 2 hydrogens here. But the problem is that as the structure becomes more complex, the number of hydrogens increasing, so it becomes difficult to interpret the structure. So the easier way is to use the line formula. So just draw 3 lines and you get the cyclopropane, right? So line formulas are very easier to draw, they're quicker to draw, and there is no complexity in drawing these simple line formulas. Right now we have seen that alkanes are saturated, cycloalkanes are also saturated, and the reactivity of the alkane and almost all of the cycloalkanes is quite similar, right? I'm not saying all cycloalkanes, I'm saying almost all cycloalkanes, but the reactivity of lower cycloalkanes are different. So what we mean by the lower cycloalkanes include cycloalkanes that have 4 carbons or less than 4 carbons. So the lower cycloalkanes include cyclopropane and cyclobutane, right? So reactivity of cyclopropane and cyclobutane is different from almost all of the cycloalkanes and the alkanes. So why we are saying that? Because all alkanes undergo substitution reactions. So they get a hydrogen substituted by some other group, but the cyclopropane and cyclobutane, they tend to undergo addition reactions. And when they undergo addition reactions, they undergo ring opening. So you have seen the addition reactions of cyclopropane with bromine, and you have seen the addition reactions of butane with bromine as well, and some other reagents as well. So whenever these systems, cyclopropane and cyclobutane, undergo addition reaction, they tend to form open chain compounds, right? So just like alkenes undergo addition reactions, cyclopropane and cyclobutane also undergo addition reactions. So we say the reactivity of cyclopropane and butane resembles more with alkenes than alkenes. So the rest of hydrocarbons, rest of cycloalkanes, they resemble more with alkenes, but cyclopropane and cyclobutane, they resemble with alkenes in their reactions. So we have to study the reason why these two hydrocarbons, these two cycloalkanes, are behaving differently. So before going to the reason of their difference in reactivity, we'll see about a concept which is known as the internal energy. The internal energy of a molecule consists of all sorts of energies which are stored in a molecule. So the internal energy include the kinetic energy of the molecule because of motion of the bonds. That also includes the potential energy of the molecule, right? So all sorts of energies of a molecule are known as internal energy. So in chemistry, whenever we say that a molecule is experiencing strain, it means the molecule is becoming unstable because of certain reason. And what are the certain reason? The certain reason is chemical structure. So if something is wrong about the chemical structure, if something is in a chemical structure makes a molecule to become unstable, we say that a molecule experiencing stress. And because of stress, the molecule has some sort of strain in it. And this strain in the molecule causes the molecule become unstable and increases its internal energy. Just remember that whenever a molecule is unstable, it will have higher strain and its internal energy will increase, right? So if a molecule is not unstable, it does not have any stress, then it will not have additional amount of internal energy. But if a molecule is strained, it has instability, then it will have extra amount of internal energy, which is known as the strain energy. So just compare the unstable molecule like a compressed spring. Just like if you compress a spring, you bring the components of the spring together, that at a certain point the components of a string, they tend to oppose the compression. They don't want to be compressed any further because they have already come too much closer. And if you try to apply some more compress, if you try to apply some more force, then a molecule will not compress to much more extent. Right? Similarly, if a molecule has some strain because the atoms are getting closer together, because of that strain, the stability will decrease, and because of the instability, the molecule will have some extra energy stored in the system. And in order to become stable, this molecule will try to open up in order to release the extra strain energy. So cyclopropane and cyclobutane are doing the same thing. They are just like compressed spring because the atoms have been brought much closer in the cyclic system. So in case of three-membered ring, the atoms are very, very close together. And because they are close together, so they are facing the repulsion of electrons of those carbon atoms, also the electrons of the hydrogens which are bonded to the carbon atoms. So because of these repulsions, the molecule is becoming unstable, its internal energy is increasing, and because it's becoming unstable, so in order to become stable, what it does, the three-membered ring tries to open up, the four-membered ring tries to open up. In case of five-membered ring or higher membered ring, there is no such strain because the atoms are far apart. There is no such repulsion. But in case the three-membered ring and four-membered ring, they have much repulsion because atoms are very much closer together. Therefore, the internal energy of these systems is higher. These systems have higher strain, and because these systems want to become stable, so in order to release the extra strain energy, they have to open up, right? So therefore, the cyclopropane and cyclobutane undergo addition reactions. So since we are considering the ring systems, we are considering the cyclic systems, right? The strain means instability. The instability of the cyclic system is known as ring strain. Right? So ring strain always occurs when the atoms are close together. And when the atoms are close together, because of their proximity, because of their nearness, right? So the system is becoming unstable. So their proximity is not favorable, because when they clump close together, then because of the repulsion, the system becomes unstable. And we do not want this ring strain. Why we are not wanting this ring strain? Because of this ring strain, the potential energy will increase. And if you just remember from the first lecture of this course, we mentioned that in order for a system to become stable, the potential energy must decrease. But here the potential energy is increasing. So whenever there is increased potential energy, the bond will store this potential energy and the ring will become unstable. It will try to open up and it will become more reactive. The ring strain of any cyclic molecule is a sum total of three types of strains. Right? The ring strain is actually a sum of angle strain, steric strain, and the torsion strain. So a simple way, if you want to determine if a ring has strain or not, is to determine its heat of combustion. Right? So if you compare the heat of combustion of a straight chain molecule and a cyclic molecule, we can determine the stability of the ring. So if heat of combustion is higher, that is indicating higher potential energy, and higher potential energy is indicating instability, and the instability is indicating the ring strain. Right? So if the heat of combustion is higher, that means the ring strain is also higher. Right? So increased ring strain results in increased potential energy. Right? Just remember, greater the stability, lower should be the potential energy. Right? So increased potential energy results in increased stability, so increased reactivity, and results in decreasing stability, and increased potential energy causes higher heat of combustion. So as I mentioned earlier, the ring strain is a combination of three types of strains: the angle strain, the torsion strain, and the steric strain. So let's consider first the angle strain. So what do we mean by the angle strain? Angle strain is also known as Bayer strain. So angle strain occurs because although all of the carbons in cycloalkanes are sp3 hybridized, but they do not have the expected ideal angle of 109.5. Right? So the angle strain results when there is a deviation from the ideal bond angle. Right? So whenever there is a deviation from ideal bond angle, you will get the angle strain or the Bayer strain. In order to calculate the angle strain, the simple formula is you just subtract the observed bond angle from the ideal angle. So the ideal angle is 109.5 and the observed angle is any angle which you have. For example, in case of cyclopropane here, so the observed angle is 60 degrees. The angle should have been 109.5 because the carbon is sp3 hybridized, but the observed angle is not 109.5 but it's 60 degrees. Right? So you can calculate the angle strain. So 109.5 minus 60 degrees, that's 49.5 degrees. So we say that cyclopropane is strained by 49.5 degrees. So 49.5 degrees is a huge angle. Right? So this is indicating that cyclopropane is a highly strained system. Strain means instability. So cyclopropane is highly unstable, and it's unstable because of this angle strain, and we say that cyclopropane has to be squeezed by 49.5 degrees in order to form this ring system. Right? So since the angles have been squeezed a lot, so atoms are very much closer, and because of this closeness of the atoms, because of this decreased bond angle, the system is highly unstable. Right? So this is known as the angle strain. So angle strain is prevalent, is mostly observed in cyclopropane and cyclobutane. So in case of the cyclopropane, the bond angle is 60 degrees, and you can calculate the angle strain, which is 49.5. And in case of cyclobutane, the bond angle is 90 degrees. Right? So there's a huge difference in bond angle of the cyclopropane and the ideal angle, and similarly cyclobutane and the ideal angle. So it is this deviation of these observed angles from the ideal angle that is causing these two cycloalkanes to become unstable. In case of the cyclohexane and cycloheptane, so they have much lower bond angle strains because the angles between the carbons are much closer to 109.5. So in case of cyclopentane, the bond angle is 108 degree. So just difference of 1.5 degree, right? So since this is very small angle difference, we say that both of these conformations, both of these cycloalkanes are strain free. So if a system is strain free, it means it is stable, it will be less reactive, right? So cyclopropane and cyclobutane are highly unstable because of this angle strain. Now we have heat of combustion. So as we say that heat of combustion values increases as the number of carbons increase, right? And the heat of combustion decreases with the ratio of heat of combustion and CH2 ratio, right? So the increase in the heat of combustion is because of higher amount of Lindner Swarian forces, right? And this decrease in CH2 is attributed to decrease in angle strain or decrease in the ring strain. So just for comparison, let's consider, so this is the heat of combustion for cycloalkane. So you can see the heat of combustion is minus 499, right? That's higher, while in case of the ratio of heat of combustion and by CH2, you can see this is 166.6 degree. So as you move lower, so the value is becoming more negative, right? So the heat of combustion is decreasing as the ring increases in its size, right? So value is becoming more negative, right? So this is a higher value, minus 499, while minus 655, that's a lower value. So as the ring becomes larger in size, then the heat of combustion, that is decreasing, right? Because system is becoming more stable. So high heat of combustion is indicating higher potential energy, and higher potential energy is indicating the higher instability, right? So the major cause of instability of cyclopropane and cyclobutane is because of that angle strain, because of which the rings are squeezed to a larger angle, right? So now we have next type of strain, which is known as the static strain. Static strain, also known as the van der Waals strain, occurs when atoms are forced to get closer than their van der Waals radii allows, right? So you know that atoms come closer together to form a bond, but if the atoms come too much closer, then they try to repel each other. Now we are considering the atoms which are not bonded together, right? The atoms must be at least 4 bonds away from each other, and they are closer to each other in 3-dimensional space. Consider these methyl groups right here. So methyl and this methyl, so they are closer in space, not much closer, but they are still closer in space. So what happens that they are repelling each other, because this hydrogen of methyl group, similarly hydrogen of methyl group, and these hydrogens from methyl group, they are very close together in 3-dimensional space. So electrons of these hydrogens of these methyl groups, they are repelling each other, right? So because of repulsion of these neighboring groups which are closer in space, this is causing a static strain. So in this case, if you are saying that these two methyl groups, although they are 1, 2, 3, 4, 5, they are 5 bonds away. Although these two groups are 5 bonds away, but they are much closer in space. I just see the strain energy in it, right? So in case when the methyl groups are closer but not that close, the strain energy is 7.6. But in this case, when the methyl groups are very close together, the strain energy is 12 to 15 kilocalories per mole, right? So if the groups or atoms are very close together, then because of their repulsion, the strain or the instability is known as the static strain, and also known as the van der Waals strain. The amount of steric strain is dependent on the size of the interacting group, right? So if you have a tertiary-butyl group is a very bulky group. So bulky group means larger group. So if a group is much larger, then the static strain will be higher, because repulsion of that group will be much more. But in case if you have a smaller group, then the static strain will be lower, right? The static strain is dependent on the size of the interacting groups. Larger the groups, more will be the static strain. Smaller the groups, lesser with steric strains. For example, you are saying that this is a very bulky group, right? So these bulky groups, they are closer to each other in space, so the steric hindrance will be much more. But these are smaller groups, right? So if we have smaller groups, then in that case the steric strain will be lower, right? The steric strain is this instability that caused when two larger groups are closer to each other in space. Right, the concept of steric strain is very important in predicting the products of a chemical reaction. Why we are saying that? Because the group of atoms that are attached to a carbon in such a way that steric hindrance is minimized, right? So there must be less crowding so that atoms don't repel each other, right? So whenever there is a compound formed, whenever there is a molecule, so in molecules the atoms are arranged in such a way that there is minimum repulsion between the atoms, or there is a minimum repulsion between the electrons of the bonded atoms, right? Therefore the chemical reaction will give a mixture of products where stable and unstable products are formed. So in certain molecules the products are more stable because the arrangement of atom is making the molecule stable, and in some other products the arrangement of atoms is not making a molecule much stable, right? The steric strain is an important concept because by seeing the structure we can see if the structure is hindered or not, so we can predict that which of the product will be major. So a product that will have maximum stability, will have minimum steric hindrance, will be the major product, while the product which has maximum steric hindrance will be least stable and will be minor product, right? So in this way, by means of steric strain, we can determine if a product of a reaction will be major or that will be minor, right? So major product is always a stable product, while minor product is always an unstable product. So in this way, the steric strain is very helpful in predicting the product of the reaction. Now we have a third type of strain, and this third type of strain is known as the torsional strain. It's also known as the eclipsing strain, right? Whether that's torsional or whether that's eclipsing strain, right? It occurs when a bond electron passes by each other when the molecule is rotating, right? Suppose we have two bonds, right? And each bond has two electrons. So if a bond is rotating, it means the electrons in it are also moving. So if two bonds, they move past by each other, so it means the electrons of the bond are passing by each other right here. So just consider this molecule. So here we are focusing on this bond of carbon with A and this bond of carbon with B, right? So here this molecule has a single bond, so because of single bond, free rotation is possible here, right? But since free rotation is possible here, this molecule is constantly rotating. Just consider that A is fixed and B is rotating here. So as this B and A at present are maximum distance, so they have minimum repulsion. But when this bond is rotating and B comes closer to A, so as B is coming closer to A, the repulsion of B and A is increasing, because this bond and this bond both are composed of electrons. So when these groups, they come closer to each other, the electrons in the bond, they tend to repel each other, right? So when these two are parallel to each other here, so we say they are eclipsing each other, right? When these two groups become parallel to each other exactly, we say that these two groups are now eclipsing each other, right? And at that place the electrons are facing each other. So in this condition the electrons are facing maximum repulsion, and we say this has maximum torsional strain or maximum eclipsing strain, right? The torsional strain occurs when the bond electrons pass each other when the molecule is rotating. In case if you are considering the torsional strain in a cyclic molecule, then this strain is known as Spitzer strain, right? So it's compulsory. The torsional strain occurs when molecule is separated by 3 bonds, right? And they are placed in such a position when two bulky groups are parallel to each other. In case of the static strain, as we saw that In case of steric strain, the atoms must not be directly bonded, and they should be at least 4 bonds away from each other. Alright, so in case of steric strain, the atoms must be closer to each other in 3-dimensional space, but for torsional strain to exist, then the two atoms must be separated by 3 bonds. So you can say A and B, they are separated by 1, 2, and 3 bonds. So for torsional strain, the atoms must be separated by 3 bonds, while in case of steric strain, the atoms must be separated by at least 4 bonds away, right? So if bulky groups are closer together, much closer together, when they become parallel to each other, we say they are eclipsing, and when they are eclipsing to each other, since the electrons are at maximum close to each other, so we will have maximum torsional strain. Right, so torsional strain or the eclipsing strain, right, this is the increase in potential energy due to repulsion between non-bonded electron pairs of atoms that are close together in space. So why we are saying non-bonding? Because the electrons of carbon and B and the carbon of A, they are not bonded to each other, but when they become parallel to each other, when these 2 bonds become parallel to each other, so electrons in here and electrons in here, they are repelling each other. Right, so torsional strain or eclipsing strain is the increase in potential energy of a molecule due to repulsion between non-bonded electron pairs of the atoms that are close in 3-dimensional space. Right, the torsional strain increases when bulky groups are closer to one another and decreases when the distance between the bulky groups increase. Right, so in a system which has a single bond, so at sometimes the torsional strain increases and sometimes it decreases depending on the relative position of the atoms. Right, so in this lecture we have studied about the reason why cyclobutane and cyclopropane behave differently. So we have seen about the strain. So what's a strain? Strain is any reason that causes a molecule to become unstable. So mostly the molecule become unstable because the atoms come close to each other. Right, so atoms must come close to each other when they form a bond, but if they come much more closer, then the repulsion predominates the attractive forces, and because of these repulsive forces, the system becomes unstable. So if there is instability in a ring system, this instability in ring system is known as ring strain. We have also studied the ring strain is of 3 types. It can be of angle strain, it can be the torsional strain, and it can be steric strain. In case of the angle strain, there is deviation of the observed angle from the ideal angle. So this is the reason because of which cyclopropane and cyclobutane, they are unstable. Right, the major reason why cyclopropane and cyclobutane are unstable is because of the angle strain, because there is large deviation of the cyclic system from the ideal bond angle. So in case of the cyclopropane, instead of having a bond angle of 109.5, it has a bond angle of 60 degree, while in case of cyclobutane, instead of having a bond angle of 109.5, it has a bond angle of 90 degree. So because of deviation, so these systems are highly unstable. The second case of the strain was the steric strain. The steric strain is because of the bulkiness of the group. So if 2 groups, they are not directly bonded to each other, but they come closer together in 3-dimensional space, then because of their closeness in 3-dimensional space, they tend to repel each other, and because of repulsion, the potential energy increases. In the third example of the torsional strain, so the atoms are directly bonded to each other, so the 2 groups are at a distance of 3 bonds, and while rotating, these groups come closer to each other in 3-dimensional space, and when they become parallel to each other, we say they are eclipsing each other. At the point of eclipsing, the repulsion of electrons become maximum because the bonds are at maximum close distance. Right, so because of this repulsion of the electrons, the system becomes unstable. So whatever be the type of strain, always remember the strain is always caused when the atoms come closer. Whether the reason is decreased angle, whether the reason is a bulky group, or whether the reason is the rotation of the bond. Always remember, whenever there is a strain, that means the atoms have come closer than is required or then is allowed, and because of the closeness, the potential energy increases. Because of increase in the potential energy, the system becomes unstable, and because of this instability, the reactivity increases. So cyclopropane and cyclobutane are majorly unstable because of the angle strain. Furthermore, they are also unstable because of the torsional strain, because the hydrogen atoms, they are closer to each other and they are repelling each other. Also they have the steric strain, because the hydrogen atoms, because they are closer to each other in space, they tend to repel each other. That's all for today's lecture. I hope you have understood it well. Thank you.